In this unit, there are two big major ideas, and those big major ideas are confidence intervals, which are covered in Chapter 10 and Chapter 11, and hypothesis tests, which are covered in Chapter 12 and Chapter 13. And each of those things, the confidence intervals and hypothesis tests, are applied to two different situations. This first situation was confidence intervals for proportions. And you identify that by seeing something like so many out of so many people believe that blah should be legal, or something like that, where you have a percentage. So if you see proportion, also think percent. Chapter 11 was finding confidence intervals for means. So if you see the word average, and if the number you have is not a proportion, you have to do the things from that chapter. Now, with proportions, we had confidence intervals for two different things. Confidence intervals for a single proportion and the difference in two proportions. And we'll do examples of both of those. For means, there were three, but really two: single population mean, paired differences, and difference in two population means. And for hypothesis testing, it was quite, and also one more thing. And in Chapter 10, when you're using proportions, you use Z-star multipliers. In Chapter 11, you use T-star multipliers. All right, hypothesis tests. Once again, Chapter 12 deals with proportions. And Chapter 13 deals with means. Same hints. When you're talking about percents, proportions, averages, means. And once again, recall that your test statistic, in this case, is a z-value equals something. In this case, your test statistic is a t-value equals something, which parallels the whole z-star, t-star idea. All right, now in this lesson, we're really going to review chapters 10 to 12 because you just did chapter 13. So just make sure that you understand the content of that chapter 13 take-home quiz really well. All right, so 10.1, example 10.1. So suppose that a survey is done to estimate the proportion of U.S. adults who think that texting while walking across an intersection in the crosswalk should be illegal. In the survey, 54%, so see that was a percent, which means we're talking about proportions, of a randomly selected sample of 1,025 individuals said that this should be illegal. So first, what is the population of interest? Who do we care about? Well, it's the proportion of U.S. adults. So we care about the population of all adults in the U.S. What is the population parameter of interest? So this is asking, is this population parameter a proportion? Is it a mean? Well, we have a percent. So the population parameter of interest is P, which is the true proportion who think texting while crosswalking in the crosswalk should be illegal. Okay, what is the sample? Well, the sample is the 1,025 randomly selected adults. And what is the value of the sample statistic? So remember that the sample statistic, this estimates the population parameter. So what was your estimate of how many people or what proportion of people think that this should be illegal? That was 54%. And to make sure that you communicate that that's an estimate, you don't say P, you say P hat equals 0.54. All right, explain what happens to the width of a confidence interval. So explain whether the width of a confidence interval will increase, decrease, or remain the same as a result of the following changes. So if you increase the confidence interval from 90 to 95%. So remember, your confidence interval is in general of the form, in all cases, your sample statistic plus or minus some multiplier times some standard error of your sample statistic. Okay, now, what will the confidence level affect? What part of that interval does that change? That changes the multiplier. And the multiplier is bigger for a higher confidence level. You have a list of common multipliers for proportions, and if you look at them, the z star for 90% confidence is less than the z star for 95% confidence. So increasing your confidence level will do what to the interval? Well, if you increase the confidence level, you increase the multiplier, which means you make the number you're adding and subtracting bigger. And of course, we're assuming that this stays the same. So if you add or subtract a bigger number, the confidence level will be wider. Okay, if your planned sample size is decreased from, and this is your answer, the first little bit there is the work, and we're going to use that for this next problem as well. A planned sample size is decreased from 500 to 100. Okay, well that affects the standard error. And if sample size goes down, standard error does what? Okay, so let's think. So in chapter 10, so say the standard error of p hat is square root p hat 1 minus p hat over n. So if you decrease the sample size to 100, you're going to make this into a bigger number. If you divide by 500 versus dividing by 100, the standard error will be smaller with 500 than 100. So if sample size goes down, standard error goes up, and so the confidence level, or confidence interval, will be wider. And these are not special things for proportions. These also apply to means. So for example, the standard error of x bar, remember that's s over root n. And same thing holds. If n goes up, standard error decreases. Or if n goes down, standard error increases. All right, in a randomly selected sample of 400 registered voters in a community, 220 individuals say they plan to vote for candidate Y in the upcoming election. So first, find the sample proportion planning to vote for candidate Y. So p hat will equal 220, say they plan to vote for candidate Y out of 400 total, which is 0.55. Find the standard error of p hat. Well, the formula for that is p hat 1 minus p hat over n, or root of 0.55, 1 minus 0.55, which is 0.45, over n. Oh, and n is 400 in this case. That comes out to be approximately 0.0249. That 9 was an 8, but it got rounded up because the next number was a 7. Determine a 95% confidence interval for the proportion of the population for whom the treatment would be successful. So remember that the confidence interval is of the form your sample statistic plus or minus your multiplier times the standard error of a sample statistic. That's just the general basic form. In our case, that's going to be our sample statistic is p hat plus or minus, because we have a proportion, our multiplier is what your textbook calls z star, times standard error of p hat. So far we have the p hat component and the standard error of p hat component. We're just missing the z star. So I'm going to use z star equal to 2 because 95% confidence. It's okay to use 1.96. As long as you show your work and your work is correct, I will give you credit for using either one of those. It doesn't matter to me. Okay, so our 95% CI, 95% confidence interval is 0.55 plus or minus 2 times 0.0249, which is 0.55 plus or minus 2 times 0.0249, 2 times 0.0249, 0.0498, 0.55 minus that number is 0.5002, 2 plus that number, 0.55 plus 0.0498 is 0.5998. Or doing some rounding, it's really about 50% to 60%. But unless I specify how to round, either of those is totally acceptable. All right, find a 98% confidence interval for the proportion of the voters who plan on voting for candidate Y. Well, in this case, our Z star will change. For 98% confidence, the Z star you use is 2.33. So same structure, p hat, which is 0.55, plus or minus our z star, which is 2.33, times 0.0249. So 0.55 plus or minus 2.33 times 0.0249. Say 0.058, that's good enough. And then 0.55 minus that number gives us 0.492. 0.55 plus that number, 0.058 gives us 0.608, or 49.2% to 60.8%. And then also notice that we increased the confidence level from 95% in problem B to 98% in problem C. And my question is, what happened to the width? And the answer is that it got wider, as it should based on what we said in example 10.2. Got wider, so the confidence interval got wider as confidence level increased. All right, next. So it is important that you kind of know where these z-star multipliers come from. So let's find the value of a z-star multiplier that would be used to compute a 97% confidence interval. So if we're computing a 97% confidence interval, here's an approximately bell-shaped curve. This is our standard normal. We need the area in the middle to be 0.97 or 97%, which gives us 3% in both tails. So 3% in both tails, or 1.5% in each. So over there is 0.015, and over here is 0.015. Okay, and usually what we do is we work with this half of the interval. And our multiplier is the value of z such that we have this area is 0.015. So we want to find the z so that the probability that our variable z, call this z star, probability that z is less than or equal to that z star is equal to 0.015. So that number right there is z star. So what you do now is you look in a z table, and you're going to have to look on the negative side. So look in a z table, and in the big old sea of numbers, find 0.015 and then get the z it comes from. Okay, so I know that if this was 0.95, the z star multiplier is 2. So that means I can look at things that are less than 2. So looking at the negative 2.1 row, you see 0.0179, okay, not small enough. Go across that, the negative 2.1 row, and you go across. Notice that when you get to 0.07, you see 0.015. So the z star we're looking for is negative 2.17. And when you get to this stage, you're almost done. The multiplier, which I'm going to recall new z star, is just positive 2.17. But that's where the area, that's where those multipliers come from. you're saying, what is this number so that that area is this, 0.015. And that probably is the trickiest thing on this test. So a study was done to determine whether there is a relationship between snoring and the risk of heart disease. Among the 1,105 snorers in the study, 85 had heart disease, while only 24 of the 1,379 non-snorers had heart disease. So calculate the proportion in each group who had heart disease. Okay, so for the snorers, we'll call that P1 hat, was 85 out of 1,105, which is approximately 0.0769. And of the non-snorers, P2 hat was 24 out of 1,379, which is about equal to 0.0174. So we're talking about 7.7% versus about 1.7%. So about 7.7% versus about 1.7%. And those numbers do seem different to me. So the question is, are they different enough to say that there actually is a difference here? And we can use a confidence interval to answer that question. So compute a 95% confidence interval that estimates the difference in proportions of non-snorers and snorers who have heart disease. I'm going to use snore minus non-snore because that keeps things positive. I will definitely specify what order to do stuff in on your exam. So we need our sample statistic plus or minus our multiplier times standard error of sample statistic. In this case, we're looking at a difference. So the sample statistic is P1 hat minus P2 hat, plus or minus our multiplier, which is again a z-star value, times the standard error of P1 hat minus P2 hat. Now we note that because we're looking at 95% confidence, z-star is equal to 2. Let's find the standard error of P1 hat minus P2 hat. Well, remember, this formula is kind of long, but here you go. It's root P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2. So in our case, that's big old root 0.0769, 1 minus 0.0769 over that population size was 1,105 plus 0.0174, 1 minus 0.0174 over that population size of 1379. And that comes out to be about 0.0088. Okay, and now we know all we have to know. So P1 hat minus P2 hat, that would be 0.0769 minus 0.0174 plus or minus 2 times 0.0088. So the 0.79 minus 0.174 is 0.0769 minus 0.0174 is 0.0595 plus or minus 2 times 0.0088, 0.0176. So 0.0595 minus that number gives us 0.0419. 2.0595 plus 0.0176 gives us 0.0771, or as percents, 4.19% to 7.71%. Okay, so what does this confidence interval mean? And on the basis of this confidence interval, can we infer that the population proportions with heart disease differ for snorers and non-snorers? So first of all, let's just write down what this means. So we are 95% confident that the difference in proportions between snorers and non-snorers who have heart disease is between what was that? 4.19% and 7.71%. In other words, between 4.19% and 7.71%, more snorers have heart disease. So can we infer that there is a difference? The answer to that question is yes. And there is a difference as the interval does not cover 0. And the crux of that is that snorers suffer heart disease at a higher rate. Than non-snorers. A survey is done to estimate the proportion of a population that favors a new tax law proposal for a city. In a randomly selected sample of 400 city residents, 43% favor the proposal. So find a 95% confidence interval for the true proportion of all city residents who favor the proposal. So first of all, our p-hat value was 0.43. That's what our sample told us. And for our 95% CI, the formula is p-hat plus or minus your z-star multiplier times the standard error of p-hat. So we know p-hat, we know that z-star is going to be 2. Let's now find the standard error of p-hat. Well, that's root p-hat, 1 minus p-hat over n. So 0.43. 1 minus 0.43 over 400 gives us about 0.0248. So 0.43 plus or minus 2 times 0.0248, which is 0.43 plus or minus 2 times 0.0248, 0.49046, 0.43 minus that number, 0.3804, 2, 0.43 plus 0.0496 is 0.4796, or 38.04% to 47.96%. All right, on the basis of the confidence interval that you found in A, can you infer that fewer than 50% of the population favors the proposed law? And remember that your confidence interval was about 38% to, let's just take a quick, to 48%, approximately. So does this suggest that less than 50% is a plausible value? The answer is yes, as the interval falls entirely below 50%. If 50% were included in the interval, then, well, that would be a plausible value, and you couldn't conclude that fewer than 50% favor that proposed law. So in a nutshell, those are the big ideas for Chapter 10. So what you have to know for Chapter 10 is how to find a confidence interval for one proportion, a confidence interval for difference in two proportions, and you need to know where the z star multipliers come from. Those are the big ideas in Chapter 10. Next, we're going to review Chapter 11, which discusses confidence intervals for means. So first, for each of the following research questions, would it make more sense to collect paired data or independent samples? Because one thing you'll have to do is distinguish, do you have a mean of paired differences, or do you just have two different populations? So women give their actual and desired weights in a survey. An estimate of the mean difference is desired. So in this sense, it would make more sense to collect paired data, as a natural pair is a person's actual and desired weight. I mean, if I weighed 115 pounds, my actual and desired weight might be the same, but if I weighed a different amount, maybe that would be different. So my actual weight and my desired weight should be paired together. 2 treatments for reducing cholesterol are compared. 40 people with high cholesterol use the first treatment, and 40 other people with high cholesterol use the second treatment. An estimate of the difference between the mean decrease for cholesterol for treatment 1 and the mean decrease for cholesterol in treatment 2 is desired. So you could theoretically design experiment B using a paired system, but there is nothing states this is paired. So no obvious pairing. So this would be 2 independent samples. And just to review, the parameter we'd be looking at here would be mu sub d. Its estimate is d bar. The parameter here we'd be looking at would be mu1 minus mu2. Its estimate, or the statistic, would be x1 bar minus x2 bar. All right, next, when we are doing confidence intervals for means, we use t-star multipliers, not z-star multipliers. So we're going to find the values of t-star for the following situations. So to do this, you use table A.2, and on your test, I'll make sure that you have all the tables that you need attached to the test. There'll be 4 of them, or 3 tables, 4 pages. So the z tables, the multipliers table, and the table 8.3 that gets you p-values for significant tests. So if your degrees of freedom are 100, and your 95% confidence level. So go to degrees of freedom is 100, 95% confidence level. The t-star multiplier that you use is 1.98. And one thing that you should note, as your sample size, which is n, as this goes up, these t-star multipliers get closer to your z-star multipliers. And remember that degrees of freedom is n minus 1. So if your sample size goes up, your degrees of freedom is going up as well. And you can see in this table, if you look at the 0.95 column, as you go down it, the multipliers get close to 1.96, which is the true multiplier for 95% confidence. And when you have an infinite number of observations, which obviously is not possible, you get 1.96. Okay, if n is equal to 41, 90% confidence level, the degrees of freedom you have is 40. In that case, the multiplier t star is for 90%, 90% confidence, degrees of freedom equals 40. I actually need like paper. 1.68. All right. Each man in a random sample of 9 men between the ages of 30 and 39 is asked to do as many sit-ups as he can in 1 minute. The mean number of sit-ups is x bar equals 35, and the standard deviation of the number of sit-ups is s equals 7. First, find the standard error of the sample mean. So standard error of x bar is s over root n, which is 7 over root 9. So 7 over 3, which is about 2.33. Next, find the 95% confidence interval for the population mean. So the form of this confidence interval is x bar, sample statistic, plus or minus multiplier, which is a t star, times the standard error of x bar. Now we need to find the t star. So to find t star, note that your degrees of freedom is 9 minus 1, or 8. And we want 95% confidence. Tells us that, looking at your table, degrees of freedom is 8, 95% confidence. The multiplier is t star equals 2.31. Okay, so we have x bar is 35 plus or minus 2.31 times the standard error of x bar, which was 2.33. 35 plus or minus 5.38. Roughly speaking, this is 29.62 to 40.38, and let's just round a whole number of sit-ups, about 30 to about 40. Okay. So with 95% confidence, the mean number of sit-ups that can be done in 1 minute for men aged 30 to 39 is between, we'll say 30 and 40 sit-ups. All right, for a sample of 20 women aged 19 to 29, responses to the question, how tall would you like to be, are recorded along with actual heights. So notice that you have ideal heights and actual heights. That's a paired sample. Okay, in the sample, the mean desired height is 66.7 inches, and the mean actual height is 64.9. The mean difference is 1.8 inches, and the standard deviation of the differences is 2.1. Find an approximate 95% confidence interval for the mean difference between desired and actual height, and write a sentence that interprets this. So the form of this interval will be d bar plus or minus your t star multiplier times the standard error of d bar. And let's just do it all in one go. D bar is 1.8. T star, okay, well, we have degrees of freedom is 19. So T star equals, I have 2.09 for 95% confidence. So plus or minus 2.09 times the standard error of d bar, which is SD, which is 2.1 over root 20. Okay, that's 1.8 plus or minus 2.09 times 0.47, or 1.8 plus or minus 0.98, which gives us 1.12 to 3.08. And we can say with 95% confidence, women want to be 1.12 to 3.08 inches taller on average. Had those numbers come out negative, that would have meant that somebody wanted to, the average was that you wanted to be shorter, not taller. Explain why the following statement is not correct. On the basis of the confidence interval we computed in part A, we can conclude that all women would like to be taller. And it's an important distinction, but these intervals talk about the average woman, not all women. So on average, women want to be taller, but there are definitely exceptions to this rule. So we can conclude that on average, women aged 18 to 29 would like to be taller. So only on average, not all. And the final example that we have is a difference. So for a sample of 36 men, the mean head circumference is 57.5 centimeters with a standard deviation of 2.4. And for a sample of 36 women, the mean head circumference is 55.3 with a standard deviation of 1.8. So find the value of the difference between the sample means for men and women. We're going to use men minus women. So this is x1 bar minus x2 bar. So first population minus second, well, first sample mean minus second sample mean. So 57.5 minus 55.3 is 2.2. So according to the data that we have, men's heads are 2.2 centimeters bigger in circumference. Find the standard error. So in this one, we're going to do the unpooled standard error, and we'll also discuss how to do the pooled standard error. Remember, you use unpooled standard error when the standard deviations are not equal. And that does refer to the true standard deviations, which you really can't know, but you can kind of guesstimate that 2.4, 1.8, in borderline, it's hard to say. So as long as you can tell me you know that, that's a sufficient thing for telling me that you know the difference between pooled and unpooled. But we're going to do the unpooled one here. So standard error of x1 bar minus x2 bar is the root of s1 squared over n1, s2 squared over n2. So s1 squared is 2.4, or 2.4 squared, over 36, plus 1.8 squared over 36 as well. And you should verify this yourself, but this comes out to be 0.5. Make sure that you can get your calculator to give you the same answer. Find an approximate 95% confidence interval. All right, so since we did the unpooled, the degrees of freedom here is actually 36 minus 1, or 35. Remember, you take the smaller of the two sample sizes, and since they're both 36, 36 is the sample size we use, minus 1. And now the t star. 35 isn't on your table, but you have 30 and you have 40, and let's just average them. The t star will be 2.03. Okay, so our confidence interval is x1 bar minus x2 bar, plus or minus, that's your statistic, plus or minus your t star multiplier times the standard error of your statistic. Notice how that has a very similar structure to other stuff you've seen. So we found that x1 bar minus x2 bar is 2.2, plus or minus 2.03 times 0.5. So that's 2.2 plus or minus, roughly speaking, 1.015 exactly. And that is 2.2 minus 1.015, so 2.2 minus 1.015 is 1.185 to 3.215. So can you infer based on this that men have bigger heads on average? The answer is yes. So men, bigger heads on average. And that's because that interval is all positive, all above 0. All right, find the pooled standard error. So, and note that the assumption here is that standard deviations are equal. And you do kind of a weighted average thing. So n1 minus 1 s1 squared plus n2 minus 1 s2 squared all over n1 plus n2 minus 2. And plugging all of our numbers in, well, 36 minus 1 will give us 35 times s1, which is 2.4 squared, also 35, 1.8 squared, but then parentheses, divided by 35 plus 35 minus 2. And make sure that you can do this in your calculator, because being able to push the buttons in the right way is actually important. This should give you about 2.12. Okay, so that's SP. Now you have to find the pooled standard error. And what that means is you do the standard error x1 bar minus x2 bar, except for with this SP instead of with s1 and s2. So SP squared over n1 and SP squared over n2. So 2.12 squared over n1, which was 36, 2.12 squared over 36, which comes out to be 0.4997. which is so awfully close to what we had in the previous problem. Find a 95% confidence interval using the pooled estimate. Okay, so here, the nice thing about pooling those estimates is it gets you a bigger degrees of freedom, which gets you a smaller multiplier. So here, the degrees of freedom is actually 35 plus 35 minus 2, which is 68. And 68 isn't on my table, so I'm just going to say that's about equal to 70. And the t star corresponding to that is 1.99. So our interval here is 2.2 plus or minus 1.99 times that 0.4997, which is about 2.2 plus or minus 0.99, or 1.21 to 3.19. And that interval is not drastically different than what we got from C. So you just have to know what the difference is between pooled standard error and, or basically what that SP, the pooled standard error thing, means, or pooled standard deviation. All right, next we have hypothesis testing. And I'm only going to review hypothesis testing for proportions because you just did the lesson on hypothesis testing for means. So for that, you should just review your notes. So suppose that the present success rate in the treatment of a particular psychiatric disorder for the relevant population is known to be 65%. A research group hopes to demonstrate that the success rate of a new treatment will be better than this standard. Use the letter P to represent the success rate of the new treatment. Write the null and alternative hypotheses. So our null hypothesis is that the success rate is no different. So P equals 0.65. And the alternative is that the success rate is better than 0.65. So P is bigger than 0.65. And just a thing to note, you always use the parameter, in this case, P, in the statement of H naught HA. I mean, here it's P, but in other cases it could be mu, it could be mu1 minus mu2, it could be P1 minus P2. But it's a statement about the true population value. Consider testing the null hypothesis that there is no relationship between smoking and getting a certain disease versus the alternative that smokers are more likely than non-smokers to get the disease. Explain in words what will be concluded about the relationship in the population if your p-value is 0.35 and the level of significance is 0.05. Well, this 0.35 is bigger than 0.05. So in this case, we would fail to reject H naught. And there is insufficient evidence to conclude that smokers are more likely than non-smokers to get this disease. Okay, the p-value is 0.04 and the level of significance is 0.05. Well, since our p-value is less than our significance level, in this case we would reject H naught and in favor of the alternative, accept HA. So in this case, we can conclude that smokers are more likely than non-smokers to get the disease. Get this disease. And just to reiterate this again, you never say H naught is true. You just fail to establish that it's false. For each of the following, calculate the z statistic. So, and also just this won't be given to you on your test, but these are z statistics because we're talking about proportions. Okay, well, the z statistic in this case is p hat minus p naught over the standard error of p naught. And remember that the standard error of p naught is given by square root p naught, 1 minus p naught over n. Okay, so let's find the standard error of p naught first, as we have to have that to do this z calculation. So in this case, sample size is 30, sample proportion is 0.7, h naught, p is equal to 0.5, which is HA that p is not 0.5. Okay, so the p naught, the null value, is 0.5. So this is root 0.5 times 0.5 over 30, which comes out to be about 0.0913. And my z value is 0.7 minus 0.5 over that number. One way to make this more accurate is this will be the last answer in your calculator. Just don't put in the rounded thing. In my case, I push second and then push the negative button on my TI 30X. Should come out to be about z equals 2.19. And thinking about where this falls, this is a normal distribution. You know that about 95% fall within 2 standard deviations. This guy is up in the top 2.5%, which does make it unusual. Once you're more than 2 standard deviations away from the mean, you're talking about a rare occurrence. All right, if the sample size is n equals 60, the sample proportion p hat equals 0.1, h naught is p equals 0.25, and HA is p is less than 0.25. Okay, so you're saying, is this fact that this is 0.1 evidence that the true p is actually less than 0.25? And it seems quite likely because 0.1 is quite different than quite far away from 0.25. So once again, let's start by finding the standard error of p naught. So that's root 0.25. 1 minus 0.25 is 0.75 over n, which is 60 in this case. Gives us about 0.0559. And our z value is, remember, that's p hat minus p naught over the standard error of p naught. And in this case, p hat is 0.1, p naught 0.25, divided by that 0.0559 gives you about negative 2.68. And if you think about the standard normal picture, there's your 95%, that's plus or minus 2 standard deviations. This guy is in the bottom 2.5%, and quite a bit over as well. So that probably is evidence that you're going to reject H naught. Once your z gets to be bigger than plus or minus 2, pretty much you're going to reject H naught. So in the previous example, we had examples of two-sided test. That was the first one. We didn't compute p-values, so that didn't matter. But 12.3a was an example of a two-sided test. And the next one was a one-sided test because the inequality just went, there was an inequality, not a not equal to. Okay, And the relationship is that the p-value, if you take the p-value for a one-sided test, you multiply it by 2 to get the p-value for the two-sided test with the same statistic, same hypothesis, same statistic, same population size, etc. So if a two-sided test for a proportion resulted in a p-value of 0.03, what would the p-value be if the test was one-sided? Well, this one had been multiplied by 2, as in gotten both tails. You just want 1. So for a one-sided test, the p-value is half of the value for a two-sided test. So in this case, it would have been 0.015. And here's a little summary. To go from one-sided to two-sided, multiply by 2. To go from two-sided to one-sided, divide by 2. A Gallup poll released on October 13th, 2000 found that 47% of the 1,052 U.S. adults surveyed classified themselves as very happy when given the choices of very happy, fairly happy, or not too happy. Suppose that a journalist who's a pessimist took advantage of this poll to write the following headline. Poll finds that U.S. adults who are very happy are in the minority, because technically you're in the minority if you're below 50%. So, that's a little bit misleading because probably there are some people who are fairly happy too. So in general, the happiness people probably are more than 50%. But anyhow, let's see what the confidence interval for this 47% is, and we'll see if this is actually justified. Okay, so the first thing is, are the conditions necessary to use a z-statistic for this test met? So those conditions are that it must be a random sample. So random sample, yes, and it must be representative. We're just going to have to assume that that's the case. And we also need to check NP and n times 1 minus p. And let's do p naught. So in this case, our null proportion would be our null proportion would be 50%. So 1,052 times 0.5 and 1,052 times 1 minus 0.5. Well, those are both bigger than 10. Find your test statistic. What we should have really done in example A is written the null and alternative hypotheses, so let's do that. So null hypothesis is that the true proportion who are very happy is 50%. So half of population is very happy. The alternative is that the proportion who are very happy is less than 50%. So a minority is very happy. And that probably is what will replace question A on your exam. Okay, next thing is to find the test statistic. So the test statistic is this z thing, which is p hat minus p naught over the standard error of p naught. And remember that the standard error of p naught is root p naught 1 minus p naught over n. So our p naught is 0.5, 1 minus 0.5 is 0.5, over n, which was 1,052. That comes out to be 0.0154. So our z statistic is 0.43 minus 0.5, oh, not 4347, excuse me, 0.47 minus 0.5 over 0.0154. Okay, so 0.47 minus 0.5 divided by 0.5 squared over 1. I got this z is negative 1.95. I actually used the very exact answer of this, so see if you can get the same thing as me. Okay. Next, find the p-value for this test. So p is the probability that you're going to observe a z-value that's less than or equal to negative 1.95. So looking at that normal picture, it's the area from negative 1.95 on down. And this will be pretty small. So this is table 8.1. That's everything for proportions is in that table. 1.95, 0.0256 is what this p-value is. And part D, on the basis of that p-value, make a conclusion. So in this case, you do indeed reject H0 and accept HA. And then just summarize in words that it is true that the proportion of people who are very happy is in the minority. It is true that the proportion of U.S. adults who were very happy in 2000 was in the minority.